students, we are going to start a new lecture. That's the lecture number 17, and this is obviously in continuation of the previous lecture, lecture number 16. And as you know, in the lecture number 16, or the last lecture, we have finished our discussions on synthesis of nanomaterials. We talked about various synthesis routes in a very brief and showed you how different ways you can produce 0-dimensional, 1, 2 and 3-dimensional nanomaterials, correct. And then not only that, we started also discussions on mechanical properties of nanomaterials, and in that I have only discussed about the basic things of mechanical behavior, mechanical properties. So today we are going to continue on that and then slowly move into what is the effect of size on the mechanical properties. So in order to give you some recap, we talked about various synthesis routes starting from top down, okay, to bottom up, and also some intermediates like mechanical alloying, other things, okay. And we also discussed something about mechanical properties, how the mechanical properties can be measured and all these aspects. That was the main thing we discussed. As you know, synthesis of nanomaterials are done mostly by top down and bottom up approaches. Top down means we start with a big material, large gun size, break it down to smaller one. Bottom up means start with molecules. Molecules comes together, they join with form clusters, and the cluster leads to formation of nanomaterials. Or you can also have intermediate things like mechanical alloying or micro machining. You can produce powders of alloys, or you can basically take chips during the machining, and that also contains nano grain sizes, and break them together and make powder. But nonetheless, in case of bottom up and in case of intermediates, you basically land up preparing powders. So you need to sinter it, or you need to consolidate it to make the product, or to make the 3-dimensional product, okay. That is the bulk nanostructured solids, and that is done basically by ultra fast sintering techniques. So a few of these techniques, like in sonochemical, which is used for 0-dimensional nanoparticle preparation, uses sound wave or ultrasonic waves. Sol gel uses the mixture of sol and gel to prepare 0-dimensional nanoparticles. Okay, you can also do molecular self assembly, like micelle kind of routes basically to prepare 0-dimensional nanomaterials. You can also prepare 1D and 2D nanomaterials by using techniques like electrodepositions, which we discussed, basically pulse electrodepositions, not electrodeposition, pulse electrodeposition, and pulse current or pulse voltage is used to prepare the nanomaterials. And this is same as like normal electrodepositions only, but you are applying a pulse voltage, correct. With high current density and usage of some kind of additives, one can actually make nice 2D nanomaterials. You can use PVD or CVD, like physical and chemical vapor depositions, to create thin films which will have nanocrystalline grains of thickness of the nanocrystalline regime. So therefore it is possible to prepare many 2D nanomaterials. Well, in terms of 3D, you can always do by melting routes like melt spinning or laser surface treatments. Okay, melt spinning is a widely used technique to prepare this kind of nanomaterials, which is, you know, we have discussed a lot on that, and this is a rapid certification route. In case of laser surface melting or laser surface treatment, you are melting a thin layer on the surface of the sample, and this thin layer basically solidifies rapidly, and that's so actually you can prepare nanomaterials, correct. And then we have discussed about some of the techniques of, you know, mechanical alloying, both at room temperature and as well as cryo temperatures. In case of mechanical alloying, you are putting powder mixture, charging the powder mixture inside a drum, rotating drum with some balls, and because of the actions of the balls and the powder mixture, you can create nanostructured materials very easily, right. And that's how then this leads to power production with nano powders. Similarly, you can do high temperature, also milling, and then which you can break down actually the powders into pieces by accelerating the fracturing process at low temperature, as well as you can actually make deformation induced nanocrystallations of the grains, okay. And this we have already discussed how it is done. You can always basically generate a lot of defects inside the grains, and these defects actually slowly align. These defects, which are nothing but dislocations, they can align and produce such a kind of nanocrystal grains easily. Okay, you can align them and prepare that. Okay, you can align them and prepare nanocrystals, and these grains actually are small Angleton boundaries. Correct. So they then slowly become high Angleton boundaries. Well, as I said, these techniques produces powder, so you need to consolidate them, and that can be done using flash sintering or spark plasma sintering. Okay, these are nothing but routes known as a fast is filled activated sintering technique. Right, that's what is widely used. Well, then you can do micro machining, which can lead to a lot of chip formation, and because of machining, shear force is pretty high. So therefore, this leads to a lot of nanocrystallization in these chips, and the chips can be ground and made powder, and the powder can be consolidated. Okay, so there are many ways of machining routes. I am not discussing again. Fine. So this is again. Then we come back to the original situations. So that's about these things. Then we discuss about some part of tensile test, how tensile tests are done, and what are the geometries you use. Okay, STM standards, and tensile test is done in a machine known as UTM, or universal testing machine. Okay, and in this case, sample is loaded into a jig and then pulled by applying forces F. Okay, and then you can actually measure this elongation as well as the load, and that can be converted to stress and strain. This is a sequence of the tensile stress specimen. Okay, now let us come back to the some of the things which you need to know. As you know, the stress is important things. Okay, the stress can be obtained by dividing the force by original area. So engineering stress is nothing but force divided by the original area. Strain, engineering strain again is same. It's basically length, increased length divided by the original length. Okay, so that's nothing but L minus L0 divided by L0. L is the length at any point of testing, and L0 is the original length. So these can also be written as delta L by L0. You can always measure the elongations at the start of the experiment, at the end of the experiments. Change of length is what is known as elongation. Okay, so that if you divide by original length, this gives you the engineering strain. Well, the typical stress strain plot will look like this. As you can clearly see, this is the stress on the y-axis, strain on the x-axis, right? And in any typical engineering materials, okay, especially metals actually show such a kind of stress strain behavior. There are two parts in this curve. One is an elastic region, other is a plastic region. In the elastic region, the stress and strain follow Hooke's law. That is, stress is proportional to strain, and we know that this can be written as by Hooke's law, okay, which is nothing but stress is equal to elastic constant multiplied by the strain. So we are not interested in this. We material scientists are mostly interested in the plastic region. Elastic region is more widely used by the structural engineers like mechanical civil engineering students, or maybe the community. But material scientists are mostly interested in the plastic aspects. So plastic portion of the curve, or plastic region of the curve, that not plastic portion, plastic is normal plastic. Here, this plastic means plastic deformation. Plastic region starts with the yield strength. That's what indicates the deviation from the linearity. This is a linear portion. Stress is proportional to strain. So any deviation from that is indicated by the yield point or yield stress, and then it goes to maxima that's corresponding to the maximum load, and that is what is known as a TS or tensile strength, and then it follows a trajectory which is going downward. Finally, the material fractures. This is same as what I showed you here. This snapshot views are reflected in terms of a stress strain plot. Correct. So in a nutshell, what you understand, that if you start deforming material, initially it will deform by elastic deformation. So, elastic deformation means any amount of strain happening in the material, if you unload, the material will go back to its original length, original size basically. But the moment you cross the yield strength, that is the point y in this curve, you are going to be a region of irreversible strain. So, you cannot, if you unload the material at any point beyond y, you will not be able to come back to the original point, that is original shape and size. It is not possible. There will be always a permanent strain remain in the material. That is the thing happen in the plastic design. And they keep on increasing these things. A lot of many things, the other things happen which we will discuss one by one. So, these are the two regions which you understand are going to happen when you test any material. So, therefore, relationship between stress and strain is given in the elastic region is by Hooke's law, and material returns to original length when the stress is removed. E is the measure of inherent stiffness of the material, and its structure intrinsic property depends on the bond strength of the atoms in the material. Its values differs for different materials. That is because of these bonding nature. Well, so and then we talked about yield point or yield point in stress strain. As the stress increases, a point appears in the stress strain curve where a linear relationship finally breaks down and material begins to yield. The yield point can be identified by the change in slope at the upper end of the linear region. Okay. Other names of the yield point is yield stress, elastic limit, proof stress, but do not worry about it. It is yield stress. So, in the plastic region, stress strain relationship no longer will be guided by Hooke's law. Load increases beyond y, elongation proceeds at a much faster rate than before, crossing the slope of the curve to change dramatically. That is what you have seen, right? You have seen that? Yes. The slope has dramatically changed, correct, from the linear region. Elongation is accompanied by uniform reduction in the cross-sectional area, consistent with the meaning maintaining constant volume. Finally, a load appears, let the load reaches a maximum value, engineering stress at this point is called the tensile strength or ultimate tensile strength. This is nothing but Ts is equal to F max by the original area, or it is also known as UTS, ultimate tensile strength. Okay, that is about the strength. What about the ductility? How do you measure ductility? Ability of any material to plastically strain without fracture is what is known as a ductility. Ductility is basically measured by terms of elongation divided by the original length. I already discussed it. So, LF minus L0 or L minus L0, whatever you define. Okay. In the earlier slide, you have defined L minus L0 by L0. LF is the final length, or L is the length at any point of time in the test, and L0 is the original length. So, LF is measures of distance between the gauge marks, as we have seen in the specimen geometry. I have shown this class also, I have shown in the last class also. Like specimen geometry as per ASTM standards has two mark on the sample. That is what is known as a gauge length. That corresponds to L0, and LF is whatever is increasing because of the application of the stress force. And then you have something known as a true stress. That was our engineering stress, engineering strain. Stress obtained by dividing the instantaneous, dividing the force by instantaneous area is known as the true stress. So, that means the sigma is equal to F by A. At any point of time in the testing, if you measure the area, that is the instantaneous area. So, instantaneous area is used to know this true stress, and F anyway you know how much force you are applying, right. So, that means you are using the actual area here, not the original area. Original area was known before the beginning of the test, but as the test goes on, the original area is changing. That is basically original area decreases because you are lengthening the sample. Fine. So, similarly, you have a true strain. True strain is nothing but written like this: G epsilon is equal to DL by L0, correct. So, if DL is a small instantaneous change of length, and if I divide it by original length, that is what is divided by the length, okay, at the time of this test, that is what is known as instantaneous change of strain or true strain. And if we integrate it over L0 to L, you get log of L by L0, that is what is your true strain. So, it gives you, provides you more realistic assessment of the instantaneous elongation per unit length, that is what it provides you. So, if you plot this two-stage two-strain curve on the top of the engineering stress strain curve, it looks like this. Okay. So, you can see here that if making does not appear, this two-stage two-strain curve will keep on moving like this, that is a dotted curve which is showing, but engineering stress strain curve will be showing a dip and then it stops at the fracture point. Am I clear? Well, now let us talk about the slope of the stress strain curve after the yield stress. If you look at this two stress increases continuously in the plastic design until nickel, okay, you can see this two stress is increasing continuously until it fractures. Okay. So, that is what you are seeing. Now, in engineering stress strain curve, the significance of this was lost because the stress was based on the original area. It means that metal is becoming more strong as the strain increases because your slope is increasing, right, and these property is known as strain hardening. What is it? So, as you see here, from here to here to here, the slope of the curve is increasing. That means it is we require more amount of stress to deform the material by specified value here, then here, or then here. That is what it is. Okay. So, that means what? Material is becoming more harder and harder. As it becomes more hard, so you need more stress to get the specified amount of deformation, and that is what is known as the strain hardening. And this is something which is very unique in metals. This happens because of the defect interaction in the material. So, if you plot this two-strain behavior, okay, if you plot two-strain behavior like this, and you can clearly see that you can measure, you can plot two-stress versus two-strain and logarithmic plot, then you can get a slope which is A by B like this, and that is what is known as the strain hardening coefficient. Okay, wow, how does it important? Because that gives you the equation of these deform curve in the plastic design, what is known as a flow curve. So, flow curve is what is you see in this plot, stress versus strain, elastic portion, then your plastic portion. The equation of this curve from here to there, or here this two stress two strain. Okay, that is what is given by flow curve. Basically, flow curve is giving you two stress two strain behavior. So, sigma and epsilon, they are related by a constant k and exponent n. This exponent is known as the strain hardening coefficients, and k is the strength coefficients, which is also material property. So, strain hardening coefficient is measured like this. So, if you plot log of two stress and log of two strain, and then you will get a straight line. That is very obvious. If I take log of ln of sigma, that is become ln of k plus n ln of epsilon. So, now if I plot log ln of sigma ln of epsilon, you get a straight line with a slope here, that is equal to ln of k, and the slope of this is basically n. That is obvious, right? That is mathematically what is possible. So, we can measure the strain hardening coefficients by this way. That is something which you should know very clearly. Now, there are different types of materials in this world. You have plastic, perfectly elastic material which has no plastic design, it goes and fractures. So, window glass is like that, you just deform it, it will fracture after the elastic limit, at the elastic limit. Okay. So, like ceramics, many cast iron, thermosetting polymers, they are like that. That is the very, then you can also have a perfectly plastic material. Okay. That means you have a elastic, and then in the plastic design the stress value remain constant. So, that means what? In the flow curve, n equal to 0 and k is equal to y. So, this flow curve k epsilon n is equal to 0, sigma become k epsilon. That means what? Sigma is basically like a constant time epsilon, sigma is proportional. That is what you see here also, you see here also. Basically, here it is constant, there is no change because k is a constant. So, therefore, for a material that will remain a flat. So, metals behave like this when heated to sufficiently high temperature. So, you may not know about decrystallization, but that is okay. High temperature, if you heat it up, it behaves like that. Otherwise, you do not see such a kind of behavior. And then you can have elastic and strain hardening behavior, which is more widely seen. Okay. More ductile metals behave like that. Here you see there is an elastic portion and there is a strain hardening portion. Okay. In fact, this looks like that. Okay, not like a straight line, but a curve, and that is the equation which is given as K epsilon dot to the power n, right. So, here flow for the flow curve K is y, K is more than y and n is always greater than 0, but n is always less than 1 also, n is not more than 1. Well, most of the cases you may not be able to measure the, do the tensile test. So, easiest way to understand or measure the mechanical property is hardness. You must know that diamond is the hardest material, because it can make scratch on anything, and talc is the softest material. That is why you apply talc on your body, not only because of flavor, but also it is very soft. So, in between there are 10 scale, like the Mohr scale, okay, MOHR. He discovered the scale from diamond to talc, there is 10 materials, and in terms of decreasing hardness. Okay. So, hardness is what? Resistance to permanent or plastic deformations. Good hardness generally means material is resistant to scratching and wear. Most tooling used in manufacturing must be hard against the scratch and the wear resistance. That is what is very, very important. And in a commonly used hardness test for assessing material property are that's why, because hardness is very quick and convenient. There are various of testing methods available, right. Most well known is Brinell and Rockwell, and also there are other tests available like Vickers, Snoop, fluoroscopes, or even durometer. So, but you need not know all of this. Vickers and Brinell is more widely used. In the Brinell hardness, what is widely used technique? You use a ball indenter and apply force on the ball, so the indenter goes and make a permanent mark in the material. Then you measure the diameter of that. Okay. Once you measure the diameter of that, then you can measure the area it makes. So, if you know the area on the sample surface will look like this. So, this is because of the ball. Okay, this is the indentation mark. So, if you know the diameter of that, you can measure the area, and if you load divide by area is what gives you the hardness. Again, this same thing, stress, correct. So, hard balls placed in the specimen surface will load 500, 1500, 3000 kgs, very high load applied. Okay. You know how to convert these kgs into load, right? If you have to multiply with by the gravity, acceleration due to gravity, right. If it is kg, you have to multiply 9.8 Newton per centimeter meter square, then only you get what is the value of the force. Brinell Hardness tester is measured like this. Okay. You see, this is what is the formula, 2f divided by pi dB, basically it is not pi dB square, okay, it is basically pi dB minus dB square minus di square, correct. That is what is widely used. Anyway, you can remember this formula, you can derive it. Rockwell hardness testing does not measure anything, it measures basically depth, does not measure area, but it measures depth. A cone shaped indenter is placed in the specimen using a minor load of 10 kilograms or even less, and that is what you can always apply higher load like 150 kilograms if you want to cause indenter to penetrate beyond the certain position. It depends on the hardness of the material also. So, then you can measure the depth, and from the depth you can calculate the hardness. So, you see that this is the indenter, and if you apply load, it make a depth. Okay, you can see that this is the depth. Sorry, this is the depth, not this one. So, this depth is what is used. For measure of hardness. Well, another important aspect I said use the shear stress. Shear stress is the frictional force exerted, in a case of fluids, but in the solid, it is these kind of stress which are applied. This force can be reduced to shear stress by dividing the area A. Okay, now let us also discuss a bit of the viscoelastic behavior, which is observed in case of polymers. Material property that determines the strain that material experiences when subject to the combination of stress and temperature over time. That is what is the viscoelastic behavior. Viscoelastic means viscous and elastic. It is a combination of viscosity and elasticity. Many of you read about polymer shows this behavior. So, this is the response of elastic material and response of a viscoelastic material. See, this is the elastic and this is the viscoelastic. So, in case of elastic material, you apply a strain and then you keep it and you drop the load, immediately it comes back. In case of viscoelastic, it increases, and once you drop it, it does not come back immediately, right. This part is missing, rather it is anelastic. It depends on the time. This relaxation depends on the time. That is why it is called viscoelastic. That is because material is so viscous, the molecules, once they stretch, they take time to come back, correct. So, although it is elastic behavior, the shape should come back to the original positions, but it takes time to come back. In case of elastic materials, it happens instantaneously. It does not take time, but in case of viscoelastic, it takes some time to come back. That is mainly because of these viscous behavior of the liquid. Although you have applied the load and the molecules have extended, they are stretched basically. So, coming back to the unstretched condition takes some time. Okay, so that is for the first part of the things in which I have discussed about various aspects of stress strain behavior of the material, how to measure it, tensile stress, hardness test, and a bit of viscoelastic behavior. Now, it is important for you to know also the defects inside the material, how these defects play a role in determining the mechanical behavior. To give an idea, perspective, why do you need the defects? If you look at any material, any crystalline material, and if you want to shear the material, and if really you want to shear the material without any defect, you require a huge stress. That is basically equal to given by G multiplied by B by twice pi A. What is why G? G is basically shear modulus, and B is this distance from one center of one atom to the other center of the other atom, and A is basically interlayer distance. Okay. So, that is how actually one can calculate. But if you look at that, this value is very high, because B by A is basically almost same, constant. B by A will be almost close to 1. So, basically that means it becomes G by twice pi, and pi is 3.14, that means it is G by 6. So, that means theoretically speaking, the material should have a strength equal to shear modulus divided by 6 or 7 basically. If you consider, that is fine, 6 to 7. But practically we do not see the material behaving showing such a high strength. Practically we see the material shows a strength of G by 100 to G by 1000. That means materials actually break much lower stress. So, then what actually happening? Why this is there is a gap between measured and the theoretically calculated value based on this model what I discussed just now. That was led to the defects in the material. So, if you look at this theoretical shear strength of material like iron, silver, even diamond and sodium chloride is very high, extremely high, and it is impossible. This is what tabulated by Kelly in his classic book Strong Solids. So, this is what the value normally you should get if you apply that formula for the theoretical shear strength. And if you look at tau max by G, that is pretty high, it is close to many cases, even in case of diamond is 24%. That is impossible to get actually real materials, because real materials have a lot of defects inside it, and these defects actually makes the material flow much earlier stress and fail also at much earlier stress. That is what it is. So, there are defects means you have point defects, which are widely, all of you know, vacancy is a point defects. You can have substitutional solute in an alloy, you can also have cell as interstitial atoms, or you can have interstitial atoms, or in case of ionic compounds you can have Frenkel defects or Schottky defects. Okay. Let us not discuss about those aspects. These defects are known as point defects. They are very important for various deformation behavior also. Well, now there are also point defects like octahedral void, tetrahedral void. These are solid atoms present in different kinds of lattices, BCC, FCC, or ACP lattices. These all you know. So you can put atoms inside this; they will act as interstitial. Interstitial is a defect. Well, sometimes the interstitial can come together and form a row of vacancies, or it can form row of interstitials. So defects can be extended also. This is all possible in case of different kinds of material. But the most important defects is the line defects. Okay. So what is the line defects? In order to understand line defects, all of you will have mattresses in your home. So whenever you want to unwrap a mattress, you just open it up. But think of just if there's a fold in the mattress and you want to remove it, so jerk it up. So you will see that fold slowly moves from one into other bench. That is what is known as a rook with a fold. Okay. So dislocation is exactly like that. Dislocation exists inside the material, and if you apply a shear force, it moves in the material. That's what happens. And this also can be compared like a caterpillar. So motion of a caterpillar. If you look at this is the caterpillar, correct? And now he wants to move from here to here. So it can jump, but it doesn't jump actually. The caterpillars are very smart guys. They want to spend least amount of energy to do that, least. So what they do? They just make a bend. If they make a bend like this, because there are thousands of legs, and then these bends actually move. You can see by bending it, it has moved from here to there, right? So this bend slowly then moves from here, there, then there, okay? And then on the straighten up, it reaches there. So dislocation also moves like that, exactly like a rook with a fold, correct? That's how actually a dislocation motion happens in a material. And they are, anyway, by the way, I already told you about dislocation. The dislocation is the most important line defect. And we will be discussing more about it in this lecture and maybe next couple of lectures also. Dislocations can be two types, edge or screw. Edge dislocations has very simple way of looking at it. They will have this is the plane and this is the line. They are perpendicular to each other. In screw dislocation, this is not true. Okay, actually, screw dislocations, the line and the plane are parallel to each other. Correct. The extra half plane, which is known as that, they are parallel to each other. Now, this can be explained in many ways, but nonetheless, dislocation motion leads to what is known as a slip, okay, or extra step. It's very clear, right? This extra plane, as it moves from here to here to here, here, and reaches the surface, it will create extra step. That's understandable. Screw also same thing. So why it is known as screw? Because it looks like a screw from the top of the dislocation. That's why it is known as a screw. So whatever you do, dislocation motion when it reaches the surface, it creates a step, and that step is known as a slip. Okay. So and by creating many such steps, you can deform a material. You can move a material from one person to another person, because it's moving by atomic columns, but still it is a movement of the material, right? So that's what is shown here. You see that this is the this is the bond broken here. This is the perfect crystal. You apply shear force, you just broken a bond and created dislocations. Okay, and then this row of atoms move to the next row. If dislocation moves here, you can see dislocation is here, dislocation is over here, and these bonds are joined. And then again this dislocation moves here, dislocation moves here, dislocation moves the surface. So it creates a step, and this is the slip plane. And this is what happens in the edge dislocation. When you move the edge dislocations from one part of the crystal to the other part of the crystals, as you can clearly see over a slip plane. So this step, what is created here at the end, this step actually known as a slip step. And this part is related to something known as a Berger vector. Okay, it is the same Berger who discovered many things. Same Berger vector who discovered many things, and it also produced shear. Okay, let me also explain to you. So that's, you have seen that this is because of the shear. Okay, shear moments, right? So shear in a macroscopic scale, if you apply shear, it can produce a partially shear region. You can see that and create a step. That's very easy. So, if you have two plates like this, if you move like that, it creates a partially shear region. That is what it does very easily, right? Very, very easily it does like that. So, now this is exactly what is true in many, many cases. Well, how does the dislocation looks in the real materials? Let us discuss about say 10 minutes or so, and we can stop this lecture. Well, dislocations cannot be seen by any other technique other than TEM actually. It can be obtained, idea can be obtained as present by different kind of microscopic techniques, but transmission electron microscopy is the only technique by which you can visualize a dislocation. That is why it took some time to see that. You can see dislocation looks like a line. This is the dislocations in a titanium, and so I am taking some pictures from such a kind of persons. Okay. So, and this is in a silicon. Silicon dislocations are more straight, but in a metal like titanium, dislocations are like a curvy. This is something is because of the nature of the material. Like in silicon, bonding is different, and then the titanium, and that is why this behavior is different. Well, you can also see some dislocations in ceramics, like in aluminum oxide or in a titanium carbide. In aluminum oxide also dislocations are curved, but that means ceramics also deform by motion of dislocations. Although they are more less ductile than metals, but deformation is observed. That is what I wanted to mean to say. Well, you know how the dislocation is generated. Dislocations are mostly generated by source or again boundaries in a polycrystalline material. That is what is normally seen in a polycrystalline material. Dislocations are generated from the gain boundaries. Gain boundaries, as we discussed a lot in our previous few lectures, in a polycrystalline material, they are the main source of dislocation generation. And here is a picture taken from Ellie Moore, okay, in a transmission microscopic images. Correct? You can see here how dislocations are getting generated from the gain boundaries very easily. So, dislocation generated from the gain boundary, then slowly moves in the gain boundary. You can see here one by one dislocations are moving inside the grain. Correct? So, there is a distance maintained between two dislocations. You can see there. Okay. This distance must be maintained because there is a stress field associated with dislocations. There is extra row of atoms, as you have seen here, extra row of atoms, and this portion is bent actually. You can clearly see atoms are bent here, extended here in this design. So, because of that, because of this nature, there will be a lot of strain. Now, strain means there will be stress field around it, and the stress field will not allow dislocations, two dislocations to come close as possible. Okay, but there is a stress field overlap, and then it is not. It will lead to increase of energy, and many things can happen. But it is not advisable or not possible rather to have these two dislocations coming closer than certain distance. In fact, the distance can be also calculated knowing the stress field and other Bazar vector and many other things. Okay. So, now the dislocation generated like this, they are moving inside the grain, correct? So, then what will happen? They will go to the next gain boundary, okay, something like this. This dislocation which are coming, they will go to the next gain boundary, and then at the gain boundary they will find an obstacle. You must be thinking why. That is very simple, because gain and gain boundary structurally are different, they are not same. Secondly, each grain are crystallography oriented differently. So, fact that this dislocation moving on this grain, that means this grain is oriented in such a way, this is the slip plane, that is why they are moving. As you know, in FCC, the slip plane is 111, right? This is the closest back plane, 111 type of planes, that is what we should do it. Okay. So, 111 type of planes are basically the slip plane, and the direction is 110, right? That is what it is. So, so in this case, if this is a FCC material, then this plane must be oriented along 111, correct? So, that means normal on this plane should be 111, but next grain may not be same. That is why next grain is not same as this grain, the orientations are different. That is how we define the different grains actually. So, because of these two aspects, one is the gain boundary structure is different, other one is that the grains are not oriented same way. So, dislocations moving in a one grain will not be able to directly move into the other grain. So, that means what? Dislocations will find grain boundary as an obstacle to move. Well, you can think, you can also imagine the dislocation can jump over and reach the other grain. That is not easy at normal temperatures. That happens only at high temperature, when dislocation can climb over a ladder or over these kind of obstacles. Just like in case of hurdle races, the person comes and jump over each hurdle and move. That is possible in dislocation at high temperature, not at normal temperatures. Okay. So, nonetheless, grain boundaries act as a pile up. So, this is a picture which is showing, you can see these are the dislocations which are going inside that grain and then comes at the grain boundary, and they could not move farther. So, they then pile up. Just like a railway station, in Indian railway stations, when some people are buying tickets, you see the piling up of the passengers, right. Passengers are standing one by one, and slowly the line is increases and the piling up happens. It is routinely seen in case of railway ticket booking centers. Okay. So, same thing happens here. So, ticket counter acts as an obstacle, correct. The moment the passenger at the front of the ticket counter buys the ticket, passenger leaves, then the line moves. But most of the cases line does not change, rarely its length remains almost constant, increases. That is because passengers are more, right. So, here dislocation is moving inside the grain, come in contact with the dislocation and stops. That is why we write this grain boundary as an obstacle and this as a pile up. But as you know, as it piles up, it creates a back stress. What is that? Very simple. If you are standing in a cube, if the front guy is little bit moving, like this, there is a stress applied to the person behind him, and this leads to a back stress. The person sitting at the further behind at the end of the line also feel a force. That is what is known as the back stress, correct. So, the resolved shear stress is acting like this and back stress is acting like this. This is known as a back stress because it is applying in the backward directions. So, two things you understand: dislocation generated from the one grain boundary here moved and reached the other side of the grain boundary and piled up. Pile up and lead to back stress. The two things you must be very clear about it, very clear about it, why these are important. Okay. Well, so this aspects look to a very important concept, what is known as a grain boundary strengthening. Okay. That means what? Grain boundaries will act as a strengthening agents. This is increasing the strength of the material. Grain boundaries are defects, but defect is leading to increase of the strength. Why? That is what I understandable here. See, this is the two grains, or this is a two grain model. You can see this is the plane, slip plane. Dislocations are moving like this, and then reach at the grain boundary, pile ups. Correct? So, in order to start the dislocation motion on the other grain, the enough stress should be applied so that the other grain start deforming and dislocation start moving. Or it should be like that the two grains have the same kind of slip planes at a certain deviation from the angle. It was like this, correct. But normally that does not happen. Slip planes will not be arranged like that way. So, therefore, dislocation will slowly pile up. As it pile ups, it creates a stress on the boundary, and this stress should reach a critical value, then it will lead to generation of dislocations or movement of dislocation on the other grain, then the formation proceeds. That is the model which is developed by Hall and Page. Okay. Two gentlemen, very famous, Hall and Page, coined this model. That grain boundaries indeed act as a strengthening agent, and this is how it happens. Now, if you go back here, that is what you see here. The dislocations are maintained at distance in the pile up and then created a back stress on the grain boundary, and if this back stress reaches a critical stress, more than a critical stress, this can lead to dislocation motion in the other grain. Once we are successful to do that, then the plastic deformation starts in the other grain and it follows up subsequent grains, correct. So, that is because that this pile up has led to a pile up happened because of this grain boundary is the reason for strengthening, correct. That is the main reason for strengthening. Well, so as you know, in a multicrystalline or nanocrystalline material with many grains, these are the grain, there are so many grain boundaries, correct, large amount of grain boundary area, and this large grain boundary area will create large amount of pile up, and that will lead to more hardening. This is expected, correct. That is what is normally observed. Now, can you model it? Yes, it is possible to model it. It is possible to develop an equation to do that, and that equation is known as Hall-Page equations. So, let me tell you atomistically what can happen. This is the grain boundary which is more open structure is the grain. So, if we generate dislocations like that, okay, if we generate dislocation like this, one here, another one, like that, you can see, then this row of dislocations gets piled up at this other grain boundary, and then in order to start the dislocation activity in this grain, the sufficient amount of stress must be generated, so that dislocation activity will start in the neighboring grain, correct. So, that stress must be more than a critical stress. This can be measured depending on the orientation of the grains also. So, let me stop here. In the next lecture, we will discuss about this aspect more, and then I will tell you how things can happen. Thank you.